Let's look at an example of a counter with unused states, and then we'll make sure it recovers. If we look at this counter, we have a present state, next state, state table, and we have a state diagram. So we go from 0 to 1, we go from 1 to 2, we go from 2 to 4, from 4 to 5, from 5 to 6, and then back to 0. So our unused states are state 3, binary 3 and a binary 7. So we'll design this counter with these unused states, and then we'll make sure the unused states recover. So if we just go through our synchronous design process, then we have to determine what our flip-flop input equations would be. And we know that using a JK flip-flop, since it can both toggle and reset and set, that could be the most efficient way to build this counter. So we've done this enough that I'll let you verify that in fact our J and K are appropriate using our excitation table. Here, for example, we'll just look at JA here. We want to go from 0 to 0. 0 to 0 is set or no toggle, is reset or no toggle. So in a reset, KA is a 1, in a no toggle it's a 0. So we don't care what K is, but J needs to be a 0 in both those scenarios. And then if we come down here, A needs to go from 0 to 1. That's either set or toggle. Set or toggle means that in both scenarios J is a 1, but K is either a 0 or a 1, so it doesn't matter what K is. And so you can use the excitation table, or you just use your understanding of the next state table for the JK flip-flop. So make sure you can come up with each of these, and then we can put these into a Karnoff map, and we can come up with our flip-flop input equations. So once we get to those flip-flop input equations, we want to make sure that our counter recovers. If we don't use don't care conditions for these scenarios, then we could end up with just more difficult equations, or for JA, KA, JB, KB, JC, and KC. So we don't want to necessarily have to force it back to state 0. We just want to know that it recovers, because it shouldn't go into those states to begin with. So our process then, a good process, is to design with don't cares and then ensure that in fact recovers. So if our counter is self-correcting, then we can use this flip-flop. So this design here, where we don't need any external circuitry, which is pretty powerful. So let's go through the process then of making sure that we recover. So we have JA is equal to B. So since JA is equal to a B, it's 1 if we're in state 3 or state 7. KA is also equal to B, and B is a 1, so that's just going to be a 1. JB is equal to C. C is a 1 in both these scenarios. KB is equal to 1. And then JC is B naught, so JC will be a 0, and KC is equal to a 1. So now if we look at our JK in this top row, when we're in present state of 3, JA and KA are both going to be 1. That's going to be a toggle. A was a 1, so A was a 0, so A will become, our next state will be a 1. If down here it was a 1, it's still requiring to toggle. It was a 1, so our next state will be a 0. For our B flip-flop, we're toggling in both state 3 and state 4 for our B flip-flop. Both these present states were 0, so both these present states were 1, so both these present states will go to 0. For C, both our present states are 1, but here we're asked to reset. So no matter what the present state was, we're just going to reset, and we see that we have state 111 is going to go to state 0 on the next clock edge. State 011 will go to state 4100 on the next clock edge. So in fact we recover, and we can use this very simple diagram to create this counter with only 3 flip-flops and no external gates.